Fine. So now another thing important to know here is that since let's take a note here. So we are now filtering in LES, and then some residue is coming out which has to be modeled, right? So I have phi, any random phi is now split into filtered plus its residue, all three random component, and the phi bar quantity depends on how much you are resolving, depends on how good the mesh is. So if you so this is actually captured, right? So this is resolved by mesh, this is modeled using SGS models, the two parts. Now depending on your mesh, your phi bar is changing, right? Let's say you take a mesh which is 100 cube in all the three directions together, n cube is 100 cube, and then you refine it into 200 cube. So your resolution is better now, right? You have added more mesh points, resolution is better, so phi bar improves. But what happens to phi double prime, the model contribution? Model contribution is now a function of mesh, correct? The mesh size itself. This is not like in the RANs. In RANs models, we did not use mesh size, correct? We use Boussinesq, which depended on eddy viscosity, which depended on velocity gradient and so on. We did not have delta x, delta y, delta z inside the model, correct? But here the model component phi double prime depends on your mesh size. Smaller the mesh size, less model contribution, right? And more being resolved. So do you achieve a grid independent solution in LES is a question. We can just take an illustration like this. Let's say I'm just taking simple mesh. Let's say this is the mesh, and I have eddy. Let's say I have one big eddy here and then one tiny eddy here. So the bigger one is captured by this mesh. Okay, the mesh is smaller than the size of the eddy, that is being resolved, and this is being this particular eddy is smaller than that. So this is SGS, right? And this is resolved. This is SGS modeled. Now if I just resolve the mesh, I am doing mesh dependency study, the same problem I will take it, and then I can say so the same problem I can say that I am taking more mesh here, I am refining the mesh, okay. Let's say I have refined the mesh here, made it tinier. Now suddenly this becomes resolved also, right? So this is also becoming, both are resolved. This is also resolved. This is obviously resolved. I did a zonal refinement there, only around that. We can do global, whatever, it doesn't matter. As long as I have refined it now this structure is being resolved, I don't have to model it. Now that means by changing the mesh size, the amount of contribution from these two components, resolved component and model component, is changing, correct? So do you get mesh independent study? By changing the mesh, amount of resolved component and modeled component changes. So the question is, can you get grid independent solution in LES? What do you think? Let's say I keep on refining this and it eventually becomes a DNS mesh. Do you get now, theoretically speaking, is your LES solution using a DNS mesh matching the actual DNS data? Does it? Why? That error is also there in the filtering part, yes. In addition to that, the HGS model depends on the mesh size. So no matter how tiny, it is still finite. It is not infinitesimally small, right? Even in the DNS mesh. So a small modeling contribution is still added on top of your resolved calculation. So theoretically speaking, LES on a DNS mesh would still not perfectly match with the DNS solution. More or less, let's say matching. It may look matching, but theoretically speaking, of course, there is no point doing an LES calculation on a DNS mesh. It's more expensive actually because you have more calculations. The modeling calculations are extra here, right? In DNS, that modeling calculations are not there, right? So obviously, it is economical to do DNS on a DNS mesh rather than LES on a DNS mesh. The whole point of doing LES is to save mesh points, make computations faster. Okay, so typically you should be able to do LES on workstations or your modern laptops, desktops. That's the idea, so that you don't need a supercomputer. If DNS mesh is, let's say, 100 million, that requires a supercomputer. If you're able to do, let's say, the same case using 5 million mesh, that you can do on your desktop or laptops today, right? So 100 million, 5 million, right? With the 5 million mesh, you can get reasonably good results. Why not? That is the idea. Okay, so that means the answer here, can you get grid independent solution in LES? No. But you should always then, in CFD, we always seek for grid independent solution. We ask for it, right? So here you cannot seek for grid independence, you have to check for grid convergence. You change the mesh size and see what is the trend. Is the trend converging? Okay, so check for, you can say in LES, check for grid convergence, not independent. Check for grid convergence, or you can say grid sensitivity. Sensitivity. It means as you refine, see how your solution is changing. Is it following some trend and acceptable? So you need to apply your mind here and then decide when to stop the refinement in LES. It's not like monotonic like in RANs. You keep on refining till the solution is coming to independent solution and stop. Okay, fine. So apart from this, yeah, so there is one more thing that I would like to talk about is, yesterday we discussed that filtering, again, a filtered quantity will not be same as the original filtered quantity, right? So we did discuss that the question is phi bar equal to phi double bar? That was the question, right? And we said it's in general no, right? I said in general the answer is no. That is phi bar is not equal to phi double bar, except in spectral filters that I'll come later. But now we can go and see a numerical argument. I'll show you both the a theoretical proof, a mathematical proof for it. We can also look at a numerical proof for this, an approximation to see. So an illustration for this is like this. Let's take a numerical illustration. Okay, so let's take data points like this. Let's say I have a mesh looking like this. This is I plus 1, I minus 1. Okay, 3 points here. Can make it like this. Data points. And now I am going to put a filtering operation about I and look at phi I bar. So I will take a filter size, let's say something like this. I am taking a filter size here called delta x. Let's say filter size is delta x. This is your filter size. What I have used is called a box filter, that I will tell when we go to filter types. Right now consider that there is a filter around this and I am computing the filtered quantity here. Okay, so let's call this phi bar is being evaluated at I. Okay, so let phi bar be evaluated at I, node I here, and I am considering a 1D filtering operation here. So consider 1D filter and also homogeneous filter. That means the filter size is constant, that is constant size. Filter size is uniform. So if I do this, then the filter phi bar, the phi bar is already evaluated. I'm going to double filter. So the phi double bar will be 1D filtering operation that I'll do, which is 1 by delta x integral minus delta x by 2 to delta x by 2. So phi bar is already evaluated. I'm doing double filtering. So I have phi bar of r. R is a spatial variable. Phi r dr here. Okay. So r is your spatial variable. R is a spatial variable. So this is nothing but I can now split this into two different integrals. 1 by delta x of integral minus delta x by 2 to 0 phi bar of r dr plus integral 0 to delta x by 2 phi bar of r dr. Now I do some numerical approximation. I use a trapezoidal rule to get this. So I can say I have a point here. I call it A, B. So I can approximate this using trapezoidal rule as these two parts are sum of phi A bar plus phi B bar. Okay. So using trapezoidal rule, I can say this is equal to 1 by delta x. This is delta x by 2 phi A bar plus delta x by 2 phi B bar. Numerical approximation here. Numerical approximation using trapezoidal rule. second order accurate. Okay. So the phi a bar also I can produce now using linear interpolation between I and I minus 1 and I and I plus 1. So I get this is equal to now this gets cancelled, delta x. So essentially this becomes half of phi a bar plus phi b bar, which is equal to half of the phi a bar, the filtered quantity at A. I can use linear interpolation and say it's 1/4 of phi I minus 1 bar plus 3/4 of phi I bar. Okay. So I say that it's 1/4 of phi I minus 1 bar plus 3/4 of phi I bar. Linear interpolation of what is a phi A bar. Okay. Plus I have the other component which is 3/4 phi I bar plus 1/4 phi I plus 1 bar. I have used linear interpolation here. The two parts are split, this two. Linear interpolation. So now if I rewrite this, I get the phi double bar is equal to, I have 3/4 of these two, so which is I get half of 2 times 3/4 phi I bar. So this is 3/2 phi I bar, correct, plus 1/4 of phi I minus 1 bar plus phi I plus 1 bar. Okay. So therefore phi double bar is now coming out to be, you will have 3/4 phi I double bar plus 1/8 of phi I minus 1 bar plus phi I plus 1 bar here. Now the question is this what phi bar is? Phi double bar is, now you can see it is not equal to phi bar alone. We started with the phi bar. Of course, this is a numerical approximation. I'll give you a mathematical proof also that these two will not be same whenever you use any filter type other than spectral filter. Okay. So now you can see the phi double bar is not phi bar, because phi bar was essentially, what was your phi bar? This is essentially nothing but 1 by delta x of this phi of r dr here. So you should have essentially got here just phi bar. So you can also write it as I here, right? So the phi I double bar is now 3/4 of phi I bar plus 1/8 of its neighbors. This is not same as phi I bar. Okay, this is a numerical illustration or a proof you can think of. We'll also have what to say, mathematical illustration for this. For that we have to understand the different filter types. Okay.